This video is part of the series related to the book Statistical Modeling with R that I wrote and was published by Oxford University Press in 2023. Today's video is going to be largely conceptual in that there will not be any solved examples. The solved examples will be left for the next video in this series. So I'm going to talk about today about a fundamental assumption of all statistical model known as the IID assumption. I'm going to explain what it means in a second. And I thought that this is a good starting point to explain the reasons for the mixed models in the Frequentist framework and the reasons for the hierarchical models in the Bayesian framework. I repeat that examples of this will be shown in the next video in this series. So the IID assumption. IID means independent and identically distributed. Let's take a closer look at what this means. So independent means that the probability of observing a given value of the response variable is unrelated to and does not affect the probability of observing any other value y sub j. Identically distributed means that there is one single probability density function with a single set of constant parameters that would be used to predict all possible values of the probability of obtaining all possible values of the response variable. So in the simplest term, this IID assumption strictly implies that there is a constant and homogeneous world over space and time. Constant and homogeneous in the sense that there is a single set of parameters that predicts the probability of observing all possible values of the response variable. That is, there is no differentiation according to the site, the sex, or any other condition, or there is no variation of the probability of observing a given value of the response variable depending on any continuous numerical explanatory variable. So it implies, therefore, that anything generating a departure from this structureless and very simple world must be included explicitly in the statistical model. The structure in the model arises because of many reasons that I'm going to outline better in the next slide. But to start, it arises because of the action of causal processes and the nature and details of data acquisition. So after accounting for many potential reasons for structure in the largest possible sense in the dataset, the residuals of a well-fitting model should be close to IID, that is, should be independent, should be identically distributed, and in all cases, as we have seen, should be close to a normal distribution. So there are at least 4 non-excluding reasons for structuring the data. First of all is experimental design. So we impose or either take advantage of the natural existence of different levels of categorical explanatory variables to make comparisons for this related to our hypothesis. For instance, we add water and compare it to the absence of water in order to assess the importance of water in the growth of plants. Therefore, we expect a difference in the parameters that involved in predicting the probability of observing certain sets of values for one condition compared to the probabilities of observing a certain set of values of the response variable for the other condition being compared. The second is that data sometimes may have a cluster structure. Cluster in the sense that data may include related observations, for instance, nests that are in a common trees, related individuals that belong to a genealogy, or other, and in these cases, all these individuals, or more generally speaking, these experimental units are unlikely to be statistically independent from each other. That is, nests from a common tree are more likely to resemble, in any variable that we measure, other nests in that tree compared to nests in different trees. The third is that there might be confounding variables. Confounding variables reflect variables that affect the response variable, but they are not the main goal of the inference. These are factors whose influence we aim to control via their quantification of their effect on the response variable. Then there may be or sampling may involve sampling over space, over time, or among individuals that belong to a genealogy. By genealogy, here I mean sets of individuals related by being descendants of a common ancestor, as in a genealogy, for instance, in the case of relatives, or genealogy in the sense of as it used in systematics. So these are sources that induce lack of independence among the rows, among the sampling units in our data sets. All these features, all these reasons for structuring the data must be explicitly included in the statistical model. So the mixed models in the Frequentist framework are called in that way because they include some categorical explanatory variables that are modeled as fixed effects and others are modeled as random effects. The numerical explanatory variables are always modeled as fixed effects. Let's have a definition for that before delving further into these issues. Fixed effects refers to the situation when the levels of a factor denote a purposeful experimental manipulation. That is, this is what we want to do. This is the levels that we are comparing, denoted by the levels of this explanatory variable, are those that are related to the specific set of hypotheses. They are the complete sets of levels that are pertinent to compare in relation to the specific hypothesis. The inference that we are going to make based on our data is strictly restricted to the levels being compared. In contrast, the random effects, the levels of a factor are randomly sampled from a larger population of levels. For instance, we may know the genotype, that the genotype of individuals affects the mean of the response variables. We know and measure that. Because of that, we know and measure the genotype of different individuals. And if we were to repeat the same experiment or observation, we would not necessarily include the same set of levels of these explanatory variables. In this case, the sample genotypes, we use them, these are categorical explanatory variables, we use them as a means of controlling the effects of this variable on the response variable so as to simplify it and obtain more precise estimates of the parameters for those effects, for those variables modeled as fixed effects. Whenever we model explanatory variable as random effects, the inference can be extended to other levels of that statistical population of possible levels. So deciding when a given factor or categorical explanatory variable is to be modeled as either a fixed or random effect often depends on the goal of the analysis, and while sometimes this is very clear, in other cases this could be a point of greater debate. So let's examine first the linear mixed models. In the linear mixed models, the response variable has a normal distribution with a given mean and a given variance, as shown in the screen, and a general matrix equation for these models, for the linear mixed models, is as follows. Has three terms. Let's define all the terms. So y is the response variable, x times x is a design matrix denoting the effects of all explanatory variables modeled as having fixed effects, and beta are the vector of estimated parameters estimated by using the maximum likelihood method. The next term, z times b, z is another design by matrix denoting whether each observation is associated with each level of the effects, the factor or factors modeled as random effects. And the b's is a vector of coefficients. This vector of coefficients as modeled as if having a normal distribution with a mean of 0 and a variance covariance matrix G. We will, in coming videos of this series, we will see what this variance covariance matrix means. But for now, let's just assume that that these coefficients B are modeled as if they have a normal distribution with a mean of 0 and a given variance. And the last term, epsilon, is the unexplained variation around its mean. We can also have generalized linear mixed models in which now the response variable belongs to one of the probability distributions belonging to the exponential family. It's written in a generalized way, such that we have the mean of this probability distribution and a dispersion parameter phi that changes depending in meaning depending on the distribution. Let's recall that the normal distribution is one one of the many distributions belonging to the exponential family. So now here, let's take an example of as if when the response variable has a gamma distribution with a given mean and a dispersion parameter phi. So in this case, we would model the log, this is the link function, of the mean of the response variable conditional on the estimating this b vector of b coefficients as the composition, the additive composition of the fixed effects and the random effects. If we were to have a response variable that is binomial, its parameter, binary response variable with a binomial distribution, its main parameter is p, the probability of observing a given value, either zeros or ones. And now we would use a logit link function in which the logit of the mean of the response variable conditional on the observation of the estimation of the coefficients b is again the linear composition of the fixed effects and the random effects. All this will be clear when we solve examples in the coming videos of this series. So what I'm saying here is that G is, generically speaking, the link function. So the composition of the fixed effects and the random effects takes place on the scale of the link functions for the generalized linear mixed models. So the fitting of these mixed models in the Frequentist framework occurs using is based on variations of the maximum likelihood approach. So one difficulty of when fitting these models is that the random effects, these beta coefficients, are not observed, are not directly observable. So they function as if they were a latent variable because they're not directly observable. So this requires a solution that was provided by a statistician, requires integrating over all possible values of b. So next I'm going to show a terribly looking equation that will be explained very quickly. So the likelihood of all the parameters involved in this model given the data is the product of the likelihoods. This is what this coefficient, this term here, the capital P, is the set of the product of all the data, is the product of each of the data sets. And here this integral here simply says that we are adding the infinitesimal contributions of all possible values of the beta of the b coefficients. These b coefficients, and here we have the fixed effects, and here we have the random effects in a sort of qualitative way. So the solution of this integral is rather complex, and there are two main cases. First of all is that when the response variable has a normal distribution, here we can obtain a rather complex formula that I'm not going to show here and use a variation of the maximum likelihood method. It's called restricted maximum likelihood. Comes with the acronym REML. In this way we iteratively estimate the parameters, all these parameters, the fixed effects, the variance of the response variable, the variance of the random effects, and the set of coefficients b. When the response variable it does not have a normal distribution, then we need we don't have a a complex formula, and we need to make a numerical approximations. There are two main, but these are not the only ones, two main methods. These are known as the adaptive Gaussian quadrature and the Laplace methods. These approximations are used to calculate the integral and to then iteratively estimate the other parameters. In the book, I provide some more intuitive explanations of all these details if you ever need or want to read it. So the definitions of mixed and random effects that are used in the Frequentist framework are plagued by many inconsistencies. So for instance, one of them is that if the random sampling of the levels of the factor model as random effects is required, so then the question arises whether we can model the country ID. Let's say we have a categorical response variable country where the 25 countries of the European Union, then in that case could we possibly model this categorical explanatory variable as a random effect, because And the question arises because obviously we are not sampling countries at random. We are using the 25 countries that there are in the European Union. Or the other case is when we model the 3 years, years 1, year 2, and year 3 of an experiment as a random effect. Of course, these are not a random sample of anything. These are just the 3 years that lasted our experiment. So Gelman, a pretty good Bayesian statistician, proposed using a simpler, more concise, and more complete terminology, calling population level and group level effects. The population level effects are effects that are constant across the data. They are valid for entire data set. And the group level effects are for effects that are variable across groups or subsets of the entire data set. So another unresolved issue involved in the modeling of categorical explanatory variables as random effects in the frequentist model involves the minimum number of levels and replicates within a level of a factor to be adequately modeled as random effects. If you ask a statistician, he or she would say that you need at least 30 or more. If you ask a biologist, there is a sort of folklore theorem or folklore attitude of using at least 5, but there is no theoretical reasons for preferring 5 or 6 or 7 or 10. So the minimum number of levels for that variable, categorical explanatory variable model as random effects, affects the bias and the precision of the estimated variance of that group level or random effect. So the smaller the number of levels, the larger the bias and the lower the precision of that variance. And that may turn out to have important consequences for the inference extracted after fitting such models. Now let's turn to hierarchical models in the Bayesian framework. So mixed or multi-level models are called in the Bayesian framework as hierarchical models. More formally speaking, a model is hierarchical when we can decompose the joint posterior distribution into a series of valid conditional probability distribution. There is a great book of Hutton and Hobbs, 2005, that I highly recommend for this purpose, to read about it. So let's recall our fundamental equation of Bayesian parameter estimation. This is the posterior distribution of the parameter given the data. This is proportional to the data given the parameters. This is the likelihood. And this is the prior distribution of the parameters, that is the values, what we know about the parameters before seeing our data. This is where our data modifies the prior distribution to give us the posterior distribution, which is the goal of Bayesian inference. So there are two main sources of uncertainty in the Bayesian framework. First of all, there is sampling variation, because our response variable is a random variable, and the likelihood is the probability of obtaining data given the parameter values. This is why we model the response variable using a probability distribution. And the second source of uncertainty is the uncertainty about the parameters, the values of the parameters and their variation across groups and over time and space. This is known, depending on the book, but this is often known as process uncertainty. So now we can conceptualize three components: the data model, the process model, and the parameter model. Here, the observed data is conditional on the process and the parameters. The process is conditional on the parameters, and the parameters are just the priors. So let's transform, therefore, our initial equation, the one shown in the previous slide, in the following way. This becomes the posterior distribution of the process and the parameters given the data is proportional to the data given the process and the parameters times the process given the parameters and the prior distribution of all the parameters. So this is the posterior distribution. This is the conditional likelihood, conditional in the sense that it's conditional on the process, on the random effects, and here is the prior at the end of the equation. So let's give an example perhaps to help make this a little bit clearer. So let's assume that the observed the data model, the observed data given the process net parameters is that the response variable follows a normal distribution. This normal distribution has two parameters, the mean and the variance. So the process model is the relationship between the mean of the response variable and, for instance, a given numerical explanatory variable. This is determined by the intercept beta 0 and the slope beta 1. And let's say also that we have a group level effect. This is known as group level intercepts or random intercepts that are modeled as if they have a normal distribution with a given mean, with a mean of 0 and a given variance. So this is the process model. So the predicted mean is conditional on these coefficients, and these coefficients are dependent on the variance of these random or group level intercepts. So the parameters, here we have all the parameters that we have in this model, which are the overall intercept, the overall slope, the variance of the variance of the response variable, and the variance of the variation, the variance of the intercept that reflects how much each group intercept differs from the population level intercept denoted as beta 0. So in this case, here we have the posterior distributions of all these parameters, which is conditional on the data. This is the likelihood, the conditional likelihood again, and these are the prior distributions for all the parameters in the model. So in this video, I very quickly sketched the mixed models and the hierarchical in the Frequentist framework and the hierarchical models in the Bayesian framework, stemming from the explanations of the basic assumption of all statistical model, which is the IID assumption, the independent and identically distributed assumption that is common to all models. I recall again that we will see examples that clarify these issues in coming videos of this series. So please take a look at the corresponding chapter, which is chapter 13 in the book, for further explanations. I thank you for your attention. I hope that this video was of interest to you.